So we've built our PIC32 circuit on a breadboard. We don't have a short, and I verified that because I've got my power indicator light still on. But there could be some circuit bugs in here still. We'll find those out once we start to program the PIC. So let's go through the process of writing some code and putting it on the PIC for the first time. We're going to be using the MPLAB Snap, which is a programmer and a debugger, to put code onto the PIC, so I better plug that in. There's a little arrow on pin 1, and I have to line that up with my MCLR pin. Okay, my red LED is still on, so I know I've still got power. So let's go through the process of writing code in the MPLABX IDE and using the PIC32 compiler to generate the hex file, and then the snap will put the hex file onto the PIC for us. So here is MPLABX IDE. This is a port of NetBeans, if you've ever used NetBeans. It's a general purpose IDE. And it's kind of a dog. I'm not a big fan. It tends to get really slow when you have a lot of programs open, but there are some advantages, which I'll show you now. So to make a project for this PIC, we go to File, New Project. And we're doing a microchip embedded chip, and we're doing a standalone project. We're not starting from some other kind of source project. Now we have to choose which PIC we're programming. So I'm going to type in PIC32MX170F and then select 256B. And the tool is the programmer. So because I've got the snap plugged in, there's a snap option. I'll say next. Now it lets me select the compilers that I've installed. We're using 2.5 this year. And then I will give this project a name. We're doing homework 4. I'm going to call this test because I've already done this. And note that it's going to put it in a location. You probably want to put this in your GitHub folder so that you can easily push it. I'm putting it just in my MPLABX project. And when I say finish, it's going to generate a new project. So in the top left window here, we see all of our projects. And then in this middle big window, that's where we'll write code. The bottom, when we hit compile, we'll get to see any compile errors. And then when we hit program, we'll get to see how the programming is doing. And then the bottom left, as we generate functions, we get to see like function navigator. So I just made this project and it's blank. If I go through and look at, say, source files, there's no source files, there's no header files. If I open linker files, that's empty. I can take a look at the make file if I want. And that's the magic of this IDE, is that it manages the make file for me, so we don't actually need to look at that. Not useful. But we do need to make some C code, right, main.c, to write some code and put it onto the PIC. So let's go to source files and right click and say new PIC32 new file.c, and I'm going to call it main, say finish. Now one thing about an IDE like this is that when we made the project, it made a project folder, an actual folder on our computer. And now when I generated this main.c, it put that C file in that folder. I can also make the project and then link a C file from another folder into the project. That tends to get a little hairy because then it has these dynamic links where it's trying to remember the location of files that, that are not in the same folder. I would recommend never dragging and dropping C files from a folder into this IDE. I would always right click and say make new, and then just copy the contents over just to be safe. Okay, the C file came in with a lot of comments and general stuff we don't care about. So I'm going to select it all and delete it, start from scratch. So now I have a blank C file. And I've provided actually a template for your code. I'm going to go copy that and I'm going to paste it in. That's in the code section of our GitHub folder. So here we see int main, and we've got some kind of generic functions that all our code always has. So we're going to turn off interrupts. We're going to tell the PIC what it's supposed to cache, how fast to run, and we're going to turn off JTAG, which is a debugger. And these are just kind of the bare minimum stuff you want to do inside of your code. Then we have set up pins A4 and B4. So eventually we'll turn them to inputs and outputs and do things there. And the purpose of this code is going to be in the infinite while loop. If the button is pushed, we will blink our LED twice. And we'll blink it at a specific rate so that we can verify that the PIC is running at the speed we think it's running at. So how fast is the PIC running? the top of this code has a bunch of kind of weird statements, pound pragma config statements. So the PIC has the ability to run at a bunch of different speeds and has a lot of options built in. And those are set with the dev config special function registers. These are registers that can only be set by the programmer, by the snap. They can't be changed dynamically in code. So by using pound pragma config, we're telling the programmer, okay, I would like to disable the debugging ability because that can slow my code down. And later on, we can enable it. I want to disable JTAG. I'm going to be using PGED1 and PGEC1 as my programming pins. I don't want programming write protection. And I've left a comment here for each of these to say what you should put there to make the PIC run at the right speed. So let's figure out, how do we figure out what word to put? We're going to replace all these X's with words. What word do we put there so that debugging is off? This is a little weird. It's not in the datasheet, right? The datasheet actually tells us the options for here, but it doesn't tell us what to put in the code because that's compiler specific. So the compiler comes with, for some reason, a config web page. Pull it up here. That it calls configuration bit settings for a specific PIC. And if you go into your XC32 folder in docs, config docs, there's a specific HTML file for every single PIC. And it's just a bunch of tables that show you what words you're allowed to put in these pound pragma config part of your code to turn things on and off. So here are all the pound pragma configs. And for instance, right now, if we look for, I don't know, JTAG, we can say JTAG is on or JTAG is off. And if JTAG is on, JTAG is enabled, and if it's off, it's disabled. So when you go back to your code, there we go, we'll replace JTAG with the word off. And we can probably guess the debug will also be off and things like that. And you'll just go through these one by one, find them in that table, and replace these things with words. And sometimes the words are a little bit more complicated than on and off. Let's find an example of that. So FNOSC. This stands for the primary oscillator. Back here, and we'll look for FNOSC. We can say FRC, meaning that it uses an internal oscillator. We generally don't use the internal oscillator on the PIC because it changes its speed as the chip warms up, so it's not as accurate. So instead, we're going to be using the primary oscillator. That's an external oscillator. That's the 8 megahertz chip that we plugged in. And we'll be using it with PLL, meaning that we're going to phase lock loop it. We're going to be making that 8 megahertz bigger with a PLL circuit that's inside of the PIC. Then later on, we'll have to use another pound pragma to determine how the PLL works. Okay, what's another one we should look at? I think this is probably the most complicated part. How to get the system clock to be 48 megahertz, which is the maximum is 50 for this chip. So how do we turn 8 megahertz into 48 megahertz? The way it works on the chip is first you divide the input, the 8 megahertz, by some number to get it in the range of 4 to 5 megahertz. And so the datasheet says that at this step, you have to turn whatever this is into something between 4 and 5. Then you get to multiply it to make it big again. Then you get to divide it to make it small again. And what we're trying to get at the end is 50 megahertz. The closest we'll be able to get is 48 megahertz. So we need to divide 8 by something to get 4 to 5. We'll multiply it by something to get it big, and then we'll divide it by something to hopefully get 48. So figure out what words go here. Let's see, it's PLL IDE. We'll go find that one. So you can do a div by 1, a div by 2, a div by 3, a div by 4, and so on. So just know that you have 8 megahertz in and you're trying to get 48 out. Okay, when we look at the folders over here, one of them is black. The one that's black or bold is the one that will compile when you hit the compile button. So here's the compile button, a hammer. And when you press that down in the bottom, the output window, we'll see the output of the compiler. And so I just got a bunch of compile errors. And I can click on one, and it'll bring me to that line, and it says, you put an X here, and X is not a valid word. And we see that we have yellow underline, and then we see we got some warnings. So the IDE is here to make it really easy to hit the build button for compile, and then see all the compile errors, and so on. Okay, I'm going to switch over to my project that already works. I'm going to right click on it and say set as main. I'm not going to show you source code because that's your homework, but I'll hit the build button, and it will go through and show me that is a successful build. And now I can hit the downwards green arrow, and that will program the PIC. So it rebuilt when I hit the downwards green arrow, and the window is going to flip over to a snap window, and now it's showing me it erased the code, it programmed, and then it verified that the code is there, and now my code is running. Okay, a lot of things could prevent the PIC from running. So let's talk about what might prevent the PIC from doing what it's supposed to do. If the PIC is not powered, so these red wires here, the VDD pins, if they're not plugged in, the PIC will not be able to program itself. If the PIC is powered, but it doesn't have the bypass capacitors, it might program, it might not program, and it might kind of misbehave. So the bypass capacitor is very important. If the VCAP capacitor is not there, it might not work. Okay, the PIC might program but not run if the oscillator is not plugged in. What else? The PIC won't be able to program if the MCLR does not have a pull-up, or if the PGD and PGC are not in the right pins. So you might see a variety of errors as you're programming. Let me know what errors you see as you go, and I'll try to guide you towards what the possible circuit errors could be, depending on what the error is. Okay, the actual program that we're going to write here is when the user button is pushed, the green light blinks twice. It's going to be on for half a second, off for half a second, on for half a second, off for half a second. By doing that, we are testing to make sure that the PIC is actually running at 48 megahertz because we're programming it based on the fact that it's 48 megahertz. If it's actually running at 16 kilohertz or whatever the default speed is, because the pragmas aren't set correctly, when you push this button, it wouldn't blink at the right speed. Okay, let me show you one more set of tricks with the that the IDE can do. I'm gonna make it so you can't see the correct code. Okay. So one difficult thing about running with these PICs is that you have to know what is the name of the special function register and what are the bit fields inside of it to manipulate the SFRs. So if we know that we're trying to make pin A1 an output pin, the register that makes it an output pin is called tris. So I can say tris A, that's the register. And bits is a field that allows me to manipulate which bits are on and off inside of A that sets the pins, the inputs and outputs. So if I say tris A bits dot, the IDE will go and look inside of the H file for me for this PIC, and it will pull out all of the possible options. So I don't have to go back to the datasheet to figure out what are the possible A pins. I could just type tris A bits dot, and then I could click on the one that I want. I could say, this is an output pin. And then I could say lat A bits dot, and the same thing, equals 1. So I just made tris A an output, and I turned it on. So if you just took 333 and you're super annoyed by constantly looking at the datasheet to figure out what are the names of bits, that's the purpose of using this IDE. It helps us through these kinds of things. I can also do something where I could right-click on this definition and say navigate, go to header. Oh, I didn't find it. Maybe say navigate, go to declaration. Oh, and it pulls open the H file for me, so I don't go searching through my compiler. And it says here are here's the structure that made lat A, and here are all the bit fields inside of lat A. So it takes a lot of the searching effort out of here. Other things, we have built-in functions like CP0 for doing delays. And the trick here is that if I start writing the name of a function, so if I say underscore CP0, and then I do control space, it'll say, here are all the functions that start with underscore CP0. Oops. These are all the built-in functions that came with the compiler. I have no idea what most of these do. But I know that there is a get count and set count. So if I start typing get, here are all the gets that are available. There's get count and there's set count and all of those things. As we start writing our own C and H files, it'll also be able to search through and find those for me. So I won't be able to, I don't have to type really long functions anymore. I can just start going underscore CP 0 underscore. And as I type more, okay, I didn't expect there to be so many similar functions there, but I can do that kind of stuff. So it's kind of like a shortcut. So play around with that in the IDE and write some code so that you can get the following action. It does nothing. The LED is off when the button is pushed. Turns on and off using the set and get functions for the core timer to get half a second on, half a second off, half a second on, half a second off every time the button is pushed.